Now we're on section 14.4, hydrolysis of salts. Here we're going to predict whether a salt solution will be acidic, basic, or neutral, calculate the concentrations of the various species in a salt solution, and describe the acid ionization of hydrated metal ions. So recall from what we talked about, a neutral solution contains equal concentrations of hydronium and hydroxide ions. And remember from chapter 4, I believe, when you react an acid and a base, you have an acid-base neutralization. Let's think back to that, to what the products of such a reaction always are. Those are a salt and water. So, fun fact, the solution that results when you do this is not necessarily neutral, even when you use stoichiometrically equivalent quantities of acid and base. So the salt that's formed, its nature is really what's going to determine if the solution that you make is acidic, basic, or neutral. If you react a strong acid with a strong base, you get a neutral solution. If you react a strong acid with a weak base, you get a weakly acidic solution. Weak acid with strong base gives you a weakly basic solution, and weak acid, weak base, you can get either or. So the best way to look at these is by looking at examples. Your book tries to kind of go through things, and it's, yeah, kind of weak. So let's look at an example. We're told aniline is an amine that is used to manufacture dyes. It's isolated as anilinium chloride, a salt prepared by the reaction of the weak base aniline and hydrochloric acid. What is the pH of a 0.233 molar solution of anilinium chloride? It's kind of fun to say, anilinium, not aluminium, anilinium. And we're given our reaction there. So were we given a KB? No. But if you were to look up the anilinium ion in Appendix H, it gives you the KB, of the anilinium ion, and it is 4.3 times 10 to the negative 10th power. But since we want pH, we're going to need our Ka, because we're looking more on the acid side. And recall that Kw is equal to Ka times Kb, so we can find Ka then. Ka equals Kw divided by Kb. So 1.0 times 10 to the negative 14 divided by 4.3 times 10 to the negative 10th. So our Ka for the anilinium ion is 2.3 times 10 to the negative 5th power. So let's go ahead and make an ice table for this reaction, as we are in an equilibrium. No water since it's a liquid. We're told we're starting with 0.233 molar of the salt, the anilinium chloride. So since the chloride here, it's just a good old spectator ion, the concentration of anilinium chloride is equal to that of the anilinium. It's a 1-to-1 ratio. And we're going to approximate our acid concentration at the start to 0 and aniline to 0. We know we're losing some X for the salt ion and gaining some X on the other products. So at equilibrium, we have 0.233 minus X, and then plus X and X over on the other side. We can also go ahead and, based off of that Ka, use the assumption that X is much less than 2.33. So using that, then we can say that Ka is equal to X times X over 0.233. And that is equal to 2.3 times 10 to the negative 5th. So going ahead and solving for X, we get that X is equal to 0.0023 molar. And that is equal to our concentration of hydronium. Based off our ice table, hydronium is equal to X. So then the pH of this is equal to the negative log of hydronium, which is 0.0023. And that gives us a pH of 2.64. So this ends up making an acidic solution when we put that salt in water. So now here's when we want to figure out the acetic acid concentration in a solution, where the acetate ion concentration is 0.050 molar and hydroxide is 2.5 times 10 to the negative 6 at equilibrium, and we're given our reaction. So when we look up the acetate ion, we're told we can find that Kb is equal, well, we know that Kb is equal to Kw over Ka, and we can find the Ka for acetic acid. Ka of acetic acid is equal to 1.8 times 10 to the negative fifth. And we know that Ka and Kb are related, so because the Ka is inversely proportional to the Kb of the conjugate base. So we can plug that in then over here. So our Kb is equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So then we get a Kb of 5.6 times 10 to the negative 10th power. So then we know that Kb is equal to the concentration of acetic acid times hydroxide over the acetate ion. And we are looking for acetic acid here. We know everything else. So we know then that the concentration of acetic acid is going to be equal to Kb times the concentration of acetate divided by the concentration of hydroxide, which is 5.6 times 10 to the negative 10th times, we're told acetate was 0.050 divided by OH, 2.5 times 10 to the negative 6th. So then we get a concentration of 1.1 times 10 to the negative 5th molar. So now we want to look at figuring out whether the salt that is formed, the salt, when we put it in water, if it's going to make an acidic, basic, or neutral solution. So starting with KBr, K is inert, okay? So nothing there. And bromide, Br minus, is the conjugate base of HBr, which is a strong acid. And so since the strong acid has basically an infinite Ka, that means its Kb is essentially 0. So there's not going to be an effect. There's going to be no real base ionization, so this is going to be neutral. The next one, NaHCO3, the sodium is inert, that doesn't affect anything. HCO3 minus, though, is an amphiprotic anion. Its Ka, if we were to look that up, is 4.7 times 10 to the negative 11th. Thus, we can find its Kb, which is 1 times 10 to the negative 14 over 4.7 times 10 to the negative 11, which is 2.3 times 10 to the negative 8th power. Kb is a lot greater than Ka, so because of that, this is basic. So to figure out if your solution for a salt is acidic or basic, you need to compare the Ka and the Kb's and look at that. For C, sodium, again, inert, doesn't do anything. HPO4 2 minus. Okay, it's amphiprotic. It has a Ka of 4.2 times 10 to the negative 13. And you can tell just by looking at that Ka that Kb is going to be way bigger. But Kb then is equal to 1 times 10 to the negative 14 over 4.2 times 10 to the negative 13. Kb is 1.6. I'm sorry, not 10 to the negative. Hold on. Oops, math error. This is why you always check your math, even when you're just you're checking stuff with the book. Sometimes the book makes mistakes. 1e to the negative 14 divided by 4.2 e to the negative 13, and we get not 1.6, 0.0238. So that is much, much greater than Ka. So this, again, like the last one, is basic. And lastly, D, NH4F. Now, NH4 plus is acidic. Okay, it gives away a proton. And F minus is basic. It's the conjugate base of HF, which is a weak acid. So the Ka of NH4 is 5.6 times 10 to the negative 10th. And the Kb of F minus is equal to 1.4 times 10 to the negative 11th. Here Ka is greater than Kb. So then this guy is going to be acidic. All right. So some metal hydrates, these are kind of fun, I'm not going to lie. So metal ions can actually function as acids in aqueous solutions, except group 1 and some of group 2. So generally group 1 and 2, we don't do this. Some of group 2 does, but we're not going to worry about that. So the ions end up covalently bonding to a fixed number of water molecules to make a complex ion. Yes, a metal is covalently bonding. So if you take aluminum nitrate and put it in water, a lot of times the reaction looks like this guy here, just straight up splitting apart into Al3 plus and NO3 minuses. But in reality, the aluminum 3 ion it actually reacts with 6 water molecules to form a stable complex ion. So the aluminum, so we have these 6 water molecules. The NO3 does break off, it does its own thing, but the aluminum ends up forming this complex with 6 water molecules, and then this complex has an overall 3 plus charge. So the charges, we still are charge balanced. But then what happens is due to this complex, the OH bonds in the water molecules bonded to aluminum end up becoming more polar than the non-bonded waters. So now they can donate hydrogen ions easier. So we have this aluminum water complex and reacting with some more water in solution, and one of these hydrogens from the water donates itself to a non-complex water to make hydronium, and then you make this aluminum water hydroxide complex now with a 2 plus charge. So there's 5 other bonded waters still, though, on this conjugate base. So those can also act as waters, or as acids, excuse me. So these are polyprotic acids. So it can do this 5 more times. Now remember, with polyprotic acids, actually you don't remember yet because polyprotic acids is the next section, but basically polyprotic meaning multiple protons. So they can donate multiple times. So now we've donated 1 proton with the first one, so we have a Ka, and then it's going to do, if it can do it a second time and have a lower Ka, and it'll keep going in steps. And this is just showing you what this aluminum complex looks like, plus when it makes the hydroxide. Now what's interesting here is the strength of the acid metal complex ions tends to increase with increasing size and decreasing size of the metal. So here's some examples going in increasing, looking at increasing charges and size. So we have at the top, we have iron 3+. Notice it's got a pretty high pKa, 2.74. So it's got a higher charge, whereas the copper is 2+, and zinc is also a 2+, but we have some size differences between copper and zinc. So you can see those pKa's changing as they form these complexes. So let's go ahead and look at an example. We want to calculate the pH of a 0.10 molar solution of aluminum chloride, which dissolves completely to give the hydrated aluminum ion, giving us that AlH2O6 3+ in solution. So the equation for this is AlH2O6 3+ aqueous plus H2O. So now we don't need to look at the aluminum chloride forming the hydrate because has nothing to do with our pH here. We are looking at the hydrate that's formed acting as an acid. Equilibrium with H3O plus Al. Let me rewrite this so it looks better and fits better. Al H2O6 3+ plus H2O H3O plus this weird complex thing. Okay, so, and the Ka, when you look this up, is 1.4 times 10 to the negative 5th power. So let's go ahead and set up our ice table. As usual, no water. We start off with 0.10 molar of the hydrate. We start off with about 0 hydronium and 0 of the hydrate hydroxide, if you I don't know what else to call it. We lose some X from our starting and gain some X for our products. So at equilibrium, 0.10 minus X, X, X. And based off of that Ka, we can go ahead and assume that X is much, much less than 0.10, so that becomes 0. And our Ka is X times X divided by 0.10 now. And that is equal to 1.4 times 10 to the negative 5th power. Solving for X, which gives us our hydronium concentration, we get 1.2 times 10 to the negative 3rd molar. And so then lastly, our pH is equal to the negative log of H3O, which is this 1.2 times 10 to the negative 3rd, and is 2.92. So this is acidic.